In part 2 of lecture 3, we will discuss system calls. There is a wide range of services that an operating system is expected to provide to users and their programs. These include loading programs into memory and starting their execution, as well as terminating them when they are finished. This last part is also necessary because the operating system needs to clean up after processes, freeing their resources so other processes can use them. Because we don't trust users and their programs to perform operations that involve physical devices, the operating system must also provide services for input-output operations, file-related operations, and communications. Last of all, we expect the operating system to perform error detection, as any good program should. Except here, it is even more crucial, because if a program fails, well, it's a problem for the user. But if the operating system fails, it's a major problem for everyone. There are some things that the operating system does, not because it makes the system run more efficiently or because it provides a service to users. These things are done to help make it easier to manage the system. Processes, including the shell or command interpreter, all use system calls to request services from the operating system. In most cases, these are written in assembly language and are called using assembly language instructions. For example, in DOS, system calls were made up of an interrupt number and a function number. The function number is loaded into the AH register, and then the program uses the int instruction to make the call to the appropriate interrupt. This is completely different from Unix, where system calls look at a C function, and with the call's parameters being passed onto the operating system. Beneath all of this, operating systems can be written in assembler or in one of several higher-level languages, although these days C and C++ are the most commonly used for operating system implementation. An operating system is responsible for all the life events of a process, so you would expect that it would include system calls for creating and terminating processes, loading and executing processes, ending and aborting processes, setting and getting their attributes, and sending a signal or having a process wait for a signal. When a Unix user uses the shell to get a program running, the process begins with the fork system call being used to make a duplicate image of the shell. The original shell process gets the duplicate's process ID number, while the duplicate gets -1, an invalid ID number. The duplicate's image in memory is then replaced by the image of the program being loaded. This is done by the execv system call. DOS was a single-tasking operating system, so it couldn't create duplicate processes when it started a program running. When the operating system was loaded, memory was occupied by the kernel and command processor, as you see in the diagram on the left. When a new program was loaded, it was read into memory and overrode a great deal of the command processor. It then loaded the instruction pointer with the starting address of the program, and the program took over. The program then had control of the CPU until there was either a runtime error causing a trap, or the program issued a system call to terminate execution. Although DOS was not a multitasking operating system, it allowed for a special type of concurrent execution, the Terminate and Stay Resident program, or TSR. These programs ran long enough to hook an interrupt and to issue a special interrupt called Terminate and Stay Resident. The operating system reserved the memory belonging to the TSR and the interrupt that was hooked determines when the TSR was reactivated. Hooking was done by placing the address of one of its subroutines within one of the hooked interrupt routines. The operating system is responsible for the life events of a file and includes the system calls that open and close it, read and write it, create and delete it. When the file is being read in a non-sequential manner, that means that its pointer will have to be repositioned to the next record to be read. This is also done by a system call. Lastly, every file has certain attributes that determines how it can be used, such as whether it is read-only, who has permission to access it, and so on. These attributes are set by system calls, and programs can get the attributes by system calls as well. The system calls for devices are independent of the ones for files, even though the files may be saved on these devices. It's important to remember that these system calls will work on different levels of data abstraction. Device system calls include requesting devices, which reserves them for a particular processor user. It also includes releasing them, reading them, writing them, and repositioning their pointers as well. There is certain information which system administrators may need in order to maintain the system properly. This would include the date and time, so the system administrator can keep track of when users log in and log out, as well as when files were created or most recently updated. It would also include the number of current users. This is important because it directly affects the workload that the computer system has to bear. The current operating system version number is important because it determines what software may or may not run on this particular software platform. Lastly, information maintenance calls include the amount of free disk space. This is important for obvious reasons. If a file system or a disk runs short of storage capacity, a user may not be able to save work or to update data files. Inter-process communications is an extremely important issue on both single processor and multi-processor systems. Occasionally, processes will have to share data and they will have to signal each other to let the other process know when to wait and when to resume operations. This is something that we will talk about at much greater length shortly. The two most commonly used models of communication are message passing and shared memory. In the message passing model, the first task is to establish a communications connection between the two processes. That means getting the name of the other party in this little cybernetic chat. If it's a process on the same system, then a getProcessID call is enough. If the process is on a different computer, then we will need a host name as well. One common type of host name might be an IP name, where IP stands for Internetwork Protocol. With this accomplished, we can now open a connection and use the operating system as a conduit to pass data and control information between the two processes. The operating system has the responsibility of maintaining the connection that the two processes use. When communications are finished, another system call is used to close the connection. In the shared memory model, the processes use an area of memory as an electronic bulletin board of sorts. The operating system's memory management system maps the same area of memory as belonging to both processes. the normal restriction that other processes cannot access a given process's memory has to be relaxed more than a little bit, so one process can access the data that the other process has written there. Sharing the same memory space, however, creates a different sort of issue. While two processes can read the same data at once without a problem, only one of them can write at a time. When that process is writing, the other process cannot touch whatever is in memory. If this restriction were not placed on our data, what the second process read would depend on the results of a race condition. Since we do not want this to be determined by a foot race to memory, we would prohibit anyone from reading an area of shared memory while another process is writing there. And any process seeking to write data in a shared memory location must wait for any reading to finish. Communications and network capabilities are commonly built into modern operating systems. That means that operating systems have to include system calls for creating and deleting communications channels, sending and receiving messages, transferring status information, and even attaching and detaching remote devices.